Okay, and so in this video, we're going to be focusing on the term differentiability. And hopefully by the time we get to the end, we'll be able to have a better understanding as what it means for a function to be differentiable or not. Now, a very simplistic way to describe the meaning of differentiability means that if I take the derivative of some function, the derivative will exist. Remember, the derivative is a limit. It's the limiting factor of the slope of the secant line in terms of the distance of the interval becoming zero. And limits, we have our restrictions in order for limits to exist, but also graphically we can look to see if the function is locally linear around the point of in question. The only issue with the graphical approach to figure out differentiability is it's hard to tell if you've zoomed in far enough to make the assumption as to whether or not the function is locally linear or not. We do know that if a function is locally linear, it will be differentiable, and vice versa. If a function is differentiable, it will be locally linear. But let's get started on some examples. So I'm given a function here. I'm given the function the absolute value of x minus 3, and I want to graph it, and I want to answer these questions off here to the left-hand side. So for part A, what is the derivative of f as x approaches 3 from the left? Well, let's graph the f of x function. So the absolute value of x minus 3, it's going to have the elbow at 3, and it's linear, so as I go to the right, it's going to increase by 1. You can always just put in numbers for x and evaluate. As I go to the left, it's going to go like this. All right, so there's our absolute value function. Now, back to part A. What is the derivative of f as x approaches 3 from the left-hand side? So I want to know what the slope is. Well, the slope as I approach 3 from the left is down 1, right 1. So this whole left-hand piece here has a derivative value that is equal to -1. So as I approach 3 from the left, the slope is -1. So f prime is going to equal -1 from that side. Now it wants me to do the same thing and say, well, what's the slope as I come at 3 from the right? Well, up 1, right 1, that means it has a slope of equal to +1. So f prime is equal to +1. And part C, is the function continuous at x is equal to c? Now remember from our first chapter, in order for a function to be continuous, it has to be defined. So f of 3 is defined as 0, and the limit as x approaches 3 from either side for this function has to equal a defined value, which as I come at 3 from the left and from the right, I come at the same point, which is at y equals 0. And so the limit exists, the function is defined, and the limit equals what the function is defined as. So yes, it is continuous at x is equal to 3. Now for part D, is f differentiable at 3? Well, in order to be differentiable, the slope from the left has to equal the slope from the right. And that does not happen. In fact, I have a sharp turn there. It's not locally linear. So the answer to this question is no. And basically, it's because my two slopes are not the same as I approach x equals 3 from either side. Because these instantaneous rate of changes, these so-called slopes, are really derivative limits. And so they don't equal each other. And the way I could write that would be that the limit as x approaches 3 from the left, because what I'm going to do is I'm going to use this limit here. The limit as x approaches c of f of x minus f of c over x minus c. That is what the derivative, one of our forms of the derivative are, f prime of c. So the limit as x approaches 3 from the left for f of x minus f of 3 over x minus 3 does not equal the limit as x approaches 3 from the right for this slope limit. Okay, let's go to the next one here. So I want to graph f of x is equal x to the 2/3 power. All right, so we can kind of work at plugging and chugging here. So we'll make our graph. So now that we have our graph of this function, we're going to look and we want to describe the derivative of f as x approaches 0 from the left and the right hand side. Well, as x approaches 0, if I try to zoom in, now my picture isn't very great, but what we have here is we have a very sharp turn. In fact, we call this we have a cusp here. We have this region where I have a very rigid turn and I go from one side, or I have a very rigid turn and my slopes are not going to be the same as I approach x is 0 from either side. Okay, so I have the graph of x to the 2/3 power here, and we'll look and see, well, what's happening as I zoom in? What kind of behavior is the graph really showing? Well, we know it has that sharp turn, but also what is happening is that as I work my way from the left-hand side or the right-hand side, I'm becoming vertical. So my slope of my tangent line is becoming undefined. So my derivative is becoming undefined because the slope of the tangent line is becoming vertical. So it's starting to approach vertical slope, vertical tangent. For the derivative, it's going to be undefined. And part B, I think we already hinted at that. Suppose you found the actual derivative equation using the formula. Well, f prime of 0 is undefined. All right, so one more example here. Now we're looking at the graph of the cubed root of x, and I made a sketch over here on the right-hand side, but let's go look at Desmos so we get a more accurate picture for what we have. And so I already have graphed this function, the cubed root of x. And let me zoom in. I don't need to see my graph. Describe the derivative of f as x approaches 0 from the left and the right. Well, as I come at 0 from the left-hand side, I'm looking at my slope here. And so the slope of that curve, as I'm getting closer and closer to 0, let me start zooming in, all right? And you look, the curve is becoming vertical. So I'm starting to have another vertical tangent. So what that means in terms of the derivative is my derivative is going to be undefined. Now, suppose we were given the actual equation for this function, for the derivative of this function. If I put in 0 into that derivative, I'm going to get it non-existent. It's going to be undefined. I'm going to have 1 divided by 0. And so we have an undefined derivative. And so what we have is we have 3 examples here of functions that are not differentiable, but they're continuous. We have a sharp turn. We have a cusp, which is you also have a sharp turn at a cusp. And then we have vertical tangents. So it's important to know, or important to note, that just because a function is continuous does not mean it is differentiable, all right? And that's kind of an important thing. We'll get a little bit more into that as we go forward. But to highlight what we're looking for graphically, functions are not going to be differentiable at points where they're not continuous, there's sharp turns, or we have a vertical tangent line. and we saw sharp turns and vertical tangent lines in our examples. A lack of continuity, that should be a no-brainer there, that we can't be differentiable if the function is not continuous. So let's actually define using limits what it means for a function to be differentiable at a point. In order to be differentiable at a point, basically what has to happen is my derivative limit has to exist. So my derivative limit
must exist.
Well, this limit that we're given is one of the forms of the derivative for finding the value of the derivative at x is equal to c. It's the alternate form. So the limit as I approach this x value from the left for my slope must equal the same slope limit as I come at it from the right. So in other words, the slope from the left has to equal the slope from the right, or the derivative from the left has to equal the derivative from the right. So let's look at two examples here. We want to find all values of x where the function is not differentiable here in the first one. So where would the function not be differentiable? So we're looking for sharp turns, vertical tangents, lack of continuity, and we'll justify why. So I'm going to start with sharp turns, or my corners. I have a corner at -6. I have a corner at -2. And those are my two sharp turns. So we'll write, I have sharp turns, indicates a lack of differentiability at x equals -6 and x equals -2. All right, so now let's look for vertical tangents. So where does the graph appear to be vertical at? It looks like it's getting vertical right here at x is equal to +2. And I don't really see anywhere else in that interval, so I'm going to say x is equal to 2. And the last thing you look for is a lack of continuity, so not continuous. So therefore, if it's not continuous, it won't be differentiable. And I see a hole at x is equal to 6. So if I'm not defined at a point, I can't be differentiable at the point. All right, now let's look at, we have the same task, but it's slightly different. So I want to find all values of x where the function is continuous but not differentiable. So where is it continuous but not differentiable? So basically I'm looking for sharp turns and vertical tangents. So let's go look for our sharp corners. I see a sharp corner here, and that's the only sharp turn I see. So I have sharp turn at x is equal to -7. That means it's not locally linear at that point. Now let's look for vertical tangents. So where does the graph appear to be vertical? And it appears to be having vertical nature right there at x is equal to -2. And because we want to be continuous, I would not include this x is equal to 3. Even though it's not differentiable, we just had the restriction that it had to be continuous, so I'm not going to make a note that the derivative doesn't exist at 3. So differentiability, and I hinted on this a little earlier in this video, differentiability applies that the function must be continuous. Because differentiability is a slope limit, and through the process of finding that limit, in order for the function to have slope, it has to be defined and continuous at those x values. So if I'm given the fact that f is differentiable at a given x value, then f must be continuous at x is equal to c. However, the converse of that statement is not always true. So just because a function is continuous at a point does not mean it's differentiable, and we just saw that in the previous example. I am continuous at my sharp turns, but I am not differentiable there. I am continuous where I have a vertical tangent line, but I am not continuous there. Okay, so we have to pay close attention to the order in which I read that for me to have a 100% always true statement. Differentiability implies that it has to be continuous. So let's look at some examples just focusing on that statement. If I'm given that a function is differentiable at x is equal to 2, tell me why the following statements have to be true. Well, The fact that it's differentiable at x is equal to 2 means that it has to be continuous. So f is differentiable at x is equal to 2, which means that it must be continuous, which also means that the limit has to exist. Part B, the reason why that statement is true is because that is the derivative limit. And so if a function is differentiable at a point, the limit that gives me the value of the derivative has to exist. Part C, f of 2 exists. Well, in order for me to be differentiable, I have to be continuous. So I have to be defined. And lastly, here in part D, the fact that I'm differentiable at x is equal to 2, we are giving the limit that finds the value of the derivative as x, or at x is equal to 2. That's just an alternate form. B and D are derivative limits. So if I'm telling you you're differentiable, that means that derivative limit has to exist. Okay, looking here at this next example, we're given a limit, and I want to make the following, or go through the following list statements to figure out which of the following has to be true. Not just sometimes true or could be true, must be true. Now, it's important to recognize what this limit is that we're given. This limit here is the derivative limit saying that f prime of -3. So the value of the derivative of x equals -3 is equal to 2. So we're given the fact that the derivative limit exists, which means it has to be differentiable at x is equal to 3, or -3. And so we're used the fact that we know it's differentiable at x is equal to -3 to figure out the following statements are true or false. So A, the limit is x, or the limit of f of x as x approaches -3 does not exist. That is false. The reason why it's false is because the fact that we are differentiable at x equals -3 means that the limit must exist. Part B, f is not defined at x is equal to -3. That is also false because the fact that we're differentiable means that the function is continuous and we have to be defined to be continuous. Part C, the derivative of f at x is equal to -3 is 2. That is a true statement because we are given the fact that we're given the limit definition of the derivative. Part D, f is continuous at x is equal to 2. That doesn't have to be true. That's false because the fact we're only given information around x is equal to -3, so that's the only assumptions we can make. And lastly, E, f of -3 is equal to 2. That's false because I don't actually know what the y value is. I only know what the slope is. All right, now let's look at determining if piecewise functions are differentiable. And these are questions you would commonly see on maybe a standardized test. So we work our way through determining if a function is differentiable. Well, to do that, step 1, see if f is continuous. And then we'll worry about the slope limit after. So to check in for continuity, I need to see if f is defined everywhere. And I'm going to look at the break, so I'm going to look at 1. And so I go put 1 in because that's my breaking x value. And I am defined at 1 on the top, so f of 1 gives me 1. Now, I need to see what the limit is. So what's the limit as x approaches 1 from the left? That would be x squared. That's going to give me 1, and I'm going to do the limit as x approaches 1 from the right, and that's going to be used to 2x plus 1, and I put 1 into there, and I get 3. So f is not continuous at x is equal to 1 because the limit doesn't exist. So therefore, it cannot be differentiable. At x is equal to 1. So we're only looking at that one point in question here. All right, so it's not differentiable at x is equal to 1 because it's not continuous. Okay, so new problem, same goal. I just changed it up a little bit here. So I want to check for differentiability. So step 1 is check for continuity. So f of 1 I put in, and that would be to put into the top equation according to the inequality, and we get 1. Now we're going to look at our limits. So the limit as x approaches 1 from the left for f of x. That's going to give me, I basically just put an x squared, I get 1. And then I want to look at the limit as x approaches 1 from the right for f of x. And so I put it into the bottom equation. That's going to be 2x minus 1. So 2 times 1 minus 1, that also gives me 1. So the limit exists because both left and right sides equal 1. And it equals what the function is defined at. So it is continuous at x is equal to 1. So step 2 is we're going to try to find the derivative. Well, because it's defined as two separate functions around x is equal to 1, we need to use we're going to have to do this derivative limit twice. And what we can do is we're going to say we're going to use the fact that f prime of c is equal to the limit as x approaches c of f of x minus f of c over x minus c. So we're going to use that limit to determine if the derivative exists or not. So we're looking around 1. So f prime of 1. So I need to look at the limit as x approaches 1 from the left, and f of x in that case is going to be x squared, so it'll be x squared minus f of c. So I put 1 into x squared and I get 1 over x minus c, so x minus 1. So there's one of my slope. That's going to be my slope from the left. And now I need to do the slope from the right-hand side. So it'll be the limit as x approaches 1 from the right for f of x, so 2x minus 1, minus f of c, so you put 1 in for x, and we get 1, over x minus 1. So I'm having to do these two limits here and then see what I get. So let's work here with the 1 on the left-hand side. I need to factor that because I put 1 in, I get an indeterminate form, 0 over 0. I have a difference of squares, so x minus 1 times x plus 1 over x minus 1. The x minus 1s will cancel, and I have the limit as x approaches 1 from the left of x plus 1. I can put 1 in at this point, and I get 2. So my derivative of the left side, this function coming from the left, is equal to 2. And we need to do the same thing for this right-handed limit. And we get the same number. So because these two limits equal each other, and I get the same value for the derivative, that means that the slope from the left side at x is equal to 1 is equal to the slope from the right side at x is equal to 1, which means the curve is locally linear. So to answer our question, Is it differentiable at x is equal to 1? It is yes, it is differentiable. So yes, differentiable at x is equal to 1.